Here we have a 3 by 3 array of unit cells of the cubic primitive lattice. Now by adding a second layer, we can get a more three-dimensional view of the cubic primitive lattice in 3 dimensions. We can also see that, for example, each of the atoms at the vertex of the unit cell counts for 1/8 because any atom at the corner is simultaneously in 8 different unit cells. Since there are 8 corners to each unit lattice for the cubic primitive cell, that means that for cubic primitive there is 1 atom per unit cell. Here we have a 2-dimensional arrangement of the body-centered cubic unit cell. To see what it looks like if we translate in both the x and the y directions. In this arrangement, we have it translated in both the x, y, and the z directions. Again, at every corner, any atom that is at the vertex of the unit cell is simultaneously in 8 different unit cells. But in body-centered cubic, you also have 1 atom that is entirely inside of each unit cell. Therefore, there are 1/8 times 8 equals 1 atom per unit cell from the vertices, and 1 from the center. So that gives us 2 atoms per unit cell for the body-centered cubic lattice. Here we have a 3 by 3 array of the face-centered cubic lattice, often called the cubic close pack, or CCP lattice. For face-centered cubic, we have 8 atoms at the vertices, so each of those counts as 1/8 because each atom at a vertex is simultaneously in 8 different unit cells, which is easier to see if you make models of the unit cells and then stack them together at a corner. For face-centered cubic, there are also 6 atoms on the faces. Each atom on a face is simultaneously in 2 different unit cells. So we count each of the face atoms as 1/2. So this gives a total of 1/8 times 8 equals 1 atom per unit cell from the corners, the vertices, and 1/2 times 6 equals 3 atoms per unit cell from the face, giving a total of 1 plus 3 equals 4 atoms per unit cell for the face-centered cubic FCC lattice. Here we have a 2-dimensional array of the tetragonal primitive lattice. And from this particular angle, it looks very similar to the cubic primitive. The difference here is that while A equals B, C is different. So A equals B not equal to C, and alpha, beta, and gamma, the angles are still all 90 degrees. To show that this is not cubic, we can turn over one of the unit cells and turn it sideways, and we see that one of the dimensions is different. So the C dimension is shorter than the A and B dimensions, so we can see it. So that's another way we can arrange the unit cells to highlight the fact that this is not cubic primitive. Again, like all the primitive unit cells, there are only atoms at the 8 corners. Each one is simultaneously in 8 different unit cells. Therefore, we end up having 1 atom per per unit cell. Here we have a slightly different two-dimensional array of the tetragonal primitive lattice, highlighting the seed length being different than the A and B length. So here we can see from the side the rectangular shape of the tetragonal lattice. Here we have one view of a more three-dimensional array of tetragonal primitive lattices. This is the body-centered tetragonal lattice. Just as in the body-centered cubic BCC, this lattice has 2 atoms per unit cell. Here we have a slightly more three-dimensional arrangement of the tetragonal body-centered lattice.